Lesson 115 is about what are called exponential functions. Exponential functions in a nutshell are when x is in the exponent. So it's a function where in the exponent you have a variable. Here's an example, 10 to the x plus 2. Now this is going to be an equation where we're solving for x. In a second, we're going to be dealing with exponential functions, which are graphs. This is going to be more like an equation you're solving for x. So let's think about this. 10 to the x plus 2 equals 17. What I need to do is rewrite 17 as 10 to a power. How do I rewrite something as 10 to a power? We've done it very recently. If I take log of 17 on my calculator, whatever number I get will be the exponent of 10 that equals 17. So here's what I mean by that. If I take log of 17, I'll get 1.23. If I rewrite that as an exponential, my base is 10. When I don't have a base, my base is 10. 10 to the 1.23 equals 17. So instead of 17 up here, I could write 10 to the 1.23 equals 10 to the x plus 2. Well, if 10 to that power equals 10 to the x plus 2, then that means these exponents have to be equal. So I can just drop the 10s and have 1.23 equals x plus 2. So my x would have to be 1.23 minus 2, which is going to be negative 0.77. So that would be your x. So when you have to solve for x and x is in the exponent, you're going to have to use logarithms in order to rewrite as an exponential function. Okay, when we have an exponential function, here's what they're going to look like on a graph. I'm going to start at some starting point and then it's going to go up to the right and it's going to grow, how we say, exponentially. You've probably seen graphs recently about the coronavirus that look like this. That's because lots of times you'll see scientific data expressed as exponential functions. Here are the two equations of these functions. 200e to the 0.4t, notice how the variable is in the exponent. E in this case is going to be the number e. So that's not a variable, that's an actual number. T is our variable. And then this one is 200e to the 0.2t. So instead of x, for exponential functions, our x-axis is going to be time, t. And then our y-axis is going to be whatever value we're looking for. So I have 200e to the 0.4t, 200e to the 0.2t. Notice how if I have a bigger number right here in front of t, it's a steeper graph. And if I have a smaller number in front of t, it's a less steep graph. With exponential functions, I have a general exponential equation where each aspect of the equation represents a certain type of number we're going to find in word problems like the one below. A sub t equals a sub o e to the kt. Here's what each part of this means. A sub t means amount after time t. So it could be, if you're talking about 10 years from now, then it would be a sub 10, whatever time, and it's the amount after that time has passed, so our new amount. A sub o is your original amount. E is just e. K is what we call the rate of change. It's a constant. And then t is going to be time. So a sub o e to the kt equals the amount after time has passed. Write that equation down, and these problems aren't super difficult if you just remember what each part of the equation means. Let's do example 2 together. It says, in the beginning, there were 400 bacteria in the dish. The number of bacteria increased exponentially. 3 days later, there were 2,000 bacteria in the dish. How many bacteria would there be in 8 days? All right, there's a lot of information in that. One thing I forgot to mention up here, when it says it increased exponentially, that's like what we saw on the last graph where it starts at a point and goes up. There is also decreasing exponentially. What that means is if it started at a point and went down instead, the way you know is if K is greater than 0, so if K is positive, then it's increase. If K is less than 0, negative, then it's decrease. So we know that if it says it increased exponentially, our K should be positive when we find it. All right, it says in the beginning there were 400 bacteria in the dish. That would go with your original amount. So A sub O is going to be 400. So we're done with that. The number of bacteria increased exponentially, okay? That just means we're going to use this equation. 3 days later, so T equals 3, there were 2,000 bacteria in the dish. So that would be the amount after 3 days, A sub T equals 2,000. How many bacteria would there be in 8 days? So we want to know A sub 8. How many bacteria? So what we need to do is use this information to find K, and then we can solve for what we're missing. So let's use this information that we have. A sub T, which is 2,000, and I'm just plugging it into this equation that we saw up here. A sub T equals A sub 0, 400, E to the K that we don't know, T, which was 3 in this case. All right, so we have 2,000 equals, well, let's just go ahead and divide by 400 on both sides. So 2,000 divided by 400 is 5. So 5 equals E to the 3K. Now what we need to do is just like we did on the first one, to get rid of to get rid of a 10 as our base, we did the log of both sides. We're going to do ln of both sides because it's an E. If I do ln of both sides, then my ln and my E cancel out. And I have ln of 5, which is 1.61, equals 3K. So if you're looking for K or T, anything in the exponent, you're going to have to use ln to get rid of that E. So then K would be 1.61 divided by 3, which is 0.54. So K equals 0.54. And remember, it's constant, so when we look for A sub 8 in just a second, we're going to use that as our K. So now let's plug back into the equation to find A sub 8. So A8 is going to equal original amount, which was still 400. Even after 8 days, the original would still be 400. E to the K, 0.54. T, which in this case is 8 days. Now this, I have nothing missing on this side. I can just plug that into my calculator and get an answer for A sub 8. So I'll do 400 times E to the power is right above ln. Use second E to the 0.54 times 8. And you should get 30,075.5 bacteria. So think about that. That's what exponential increase is. It started with 400 and 8 days later there were 30,000 bacteria. So exponential equations are used a lot for things like bacteria, and we're going to see decrease in just a second. So if you keep this equation handy and you know what each part stands for, these problems are not super bad. Example 3 says, in the beginning, there were 4.25 ounces of radioactive material. It decayed exponentially. 10 years later, 3.92 ounces remained. How much would remain after 30 years? All right, in the beginning, that's your cue for original amount, 4.25 ounces. So AO equals 4.25. It decayed exponentially. That just tells you to use the equation. 10 years later, so when T equals 10, 3.92 ounces remained. So A sub 10 equals 3.92. How much would remain after 30 years? So A sub 30 equals question mark. We don't know. So again, we're going to find K. So A sub T, 3.92, equals original amount, 4.25, E to the K times T, which is 10. So you just plug in what they give you. We're going to find K, and then we're going to use that to solve for the second thing that they give you. All right, divide both sides by 4.25. 3.92 divided by 4.25, 0.92. So 0.92 equals E to the 10K. Take the ln of both sides. ln of 0.92 equals negative 0.08. Negative 0.08 equals 10K. So when I take ln of both sides, that E goes away and I'm left with the exponent. And then divide that by 10, negative 0.008. So K equals negative 0.008. Now notice how it's negative, which fits with what they said. It decays exponentially, which means it's going away over time. So negative K means it's going away over time instead of increasing. All right, so now we're going to use this K and this time, and we're going to look for A sub 30. So A 30 would equal original amount, 4.25, E to the K, negative 0.008, times T, which in this case is 30. And then again, there's nothing missing over here, so we can just plug that into our calculator. 4.25 E to the negative 0.008 times 30. 3.34 ounces. So not much has gone away in 30 years. 4.25 was your beginning amount and 3.34 is what's left. So the radioactive material is decaying slowly. There's one more way we can use exponential functions pretty easily, and that's to measure compound interest over time in like a savings account at a bank. And there's a formula for compound interest. Instead of using A sub 0, we're going to use P, which stands for principal. And all that means, principal is the amount that's deposited in the account at the very beginning. So it is the original amount. And then the formula is going to be basically the same. We call these PERT equations a lot, P-E-R-T, because that's the equation. So AT, which is the amount after time has passed, equals P, principal, times E to the R, and in this case, R is going to be your interest rate. And then T is still your time. So these problems are very similar, it's just using money instead of things like bacteria. For our last example, let's use this compound interest equation to solve. Says Roger deposited $5,000 in an interest-bearing account that paid 7.5% interest compounded continuously. How much money did he have in 10 years? All right, so he deposited $5,000. Our principal is $5,000, and we want to see after 10 years, was it a good interest rate? Did he make a bunch of money or not? So 7.5% interest compounded continuously. So our R is going to be 7.5%, which we need to change. So 7.5%, we need to change that to a decimal in order to use it. So that'll be 0.075 is going to be our interest rate. And then how much money did he have in 10 years? So our T is going to be 10. We don't have anything missing in this equation. We can just solve. So the amount after 10 years is going to equal original amount, principal, times e to the 0.075 times 10. Now make sure when you're typing in your calculator to keep both of those in the exponent. I didn't say that before now, but that is really important. Make sure your 10's not at the end. So we have nothing missing over here, so we can just type that into our equation or into our calculator and see if he made any money. So 5,000 e to the 0.075 times 10, 10,585.00. So that's how much money he had after 10 years. It like over doubled. That's not bad at all. So anyway, use those equations and see what they give you in the problem, see what you're missing, solve for what you're missing, and these should be fairly simple.